start.
Okay.
Okay.
Okay, so can we start? Okay, so
How long are we going, by the way?
it's around 1 hour. Is it okay for you?
Yeah. Well, that's a lot today for me, but maybe can we do a little less than 1 hour, please?
Okay, we can try to skip some of the question.
Yeah. Thank you.
Okay,
Okay.
so first of all, let us introduce. So I am Anirban Roy. I am doing PhD at CISA in Trieste in Italy, and I'm working on cosmic microwave background and large scale structure formation. So Rifat, please introduce yourself.
Uh, okay. I am Ahmed Abdullah Rifat, studying with computer science engineering at Jahangir University, Bangladesh. Currently, I am working as the editor of Open Space, the upcoming magazine, Astronomy magazine from Bangladesh. Okay.
Arnav, please introduce yourself.
Hello, I am Orno from India. I am working in radio astronomy. I am from IIT.
So we are very lucky to have Professor Krauss among us, and it is my pleasure because I have studied your book. I've just read your book, and I personally know your work. So I am very delighted. But for the audience, general audience, let me introduce Professor Krauss. So Professor Krauss received his PhD degree from MIT in 1982, and then he joined Harvard Society of Fellows from 1982 to 1985. After that, he worked as an assistant professor at Yale University and later as an associate professor until 1993. Later, he moved to Case Western Reserve University, and currently he is working as a professor in School of Earth and Space Exploration and the Department of Physics in Arizona State University. He is also the director of Origin Project, which aim to find the answers of most fundamental questions about our origins, like origin of universe and origin of life, as well as the complex structure of consciousness. Professor Krauss did his research on various topics of astrophysics and cosmology. His publications mainly on the dark energy and dark matter, cosmic microwave background, and also the galaxies cluster and galaxy lensing also. Besides academic research, we are all familiar about his public lecture, I think, and also the debate. He wrote many books on physics and astronomy, as well as also on the religion and philosophy. A universe from nothing, fear of physics, and quantum men are few among them, which I personally liked. He won many awards for his scientific contribution as well as for the popularization of science. Some of them are in 2001. He won prize, the Julius Edgar Prize from the American Physical Society, and in 2003 he won the Oersted Medal from American Association of Physics Teachers and Public Service Medal in 2012 from National Science Board in USA, and many more. So if you are interested to know more about him, just search his name on Google and you will find almost everything. So
Everything.
yeah,
Okay.
I cannot take all the name of the awards, so it's okay. So in general, so it is our second episode. So first episode we did with Professor Martin Rich. So first 2-3 questions we ask very common question about your life. So Professor, when you decided to study astronomy and why you are attracted towards it, it will be good if you start from the school days because all the school students are also listening.
Okay. Well, I got interested in science when I was young for a variety of reasons. First of all, I should say that my mother wanted me to be a doctor, but she made the mistake of telling me that doctors were scientists. So I got interested in science, but I started to get interested in physics or fundamental science, probably by reading. Certainly by reading. And I remember reading a book about Galileo when I was 10 or 11 or 12 that had a big impact. And then reading other books by scientists like Albert Einstein and George Gamow and Richard Feynman. When I was in high school, a teacher gave me a book by Richard Feynman called The Character of Physical Law that had a big impact on me. And that's one of the reasons why I write books in return, I think, because those things got me turned on to science. and it's a great pleasure when I hear from young people, or maybe now not so young people, that a book of mine made them want to study science. So I think those are some of the reasons I got involved interested in science. Now, when you say astronomy, it's rather interesting, and I think this is important for the students to hear, that I studied mathematics and physics and did my PhD essentially in particle physics at MIT. I've been a professor of astronomy as well as physics for over 30 years, but I never took a single astronomy course in my life. I think it's important. I realized that the universe was a wonderful place to test fundamental physics, and so I started to learn about cosmology and astronomy, and in order to understand things like dark matter, dark energy, and other fundamental ways of testing our ideas of the fundamental structure of matter and energy. And so I think it's really important to realize that it's a lifelong learning process. So as I say, I've been a professor of astronomy, but everything I know about astronomy I've learned after my PhD, or almost everything. And so I consider myself a physicist who dabbles in astronomy, if you want, rather than an astronomer. But I like to study anything that sheds light on ways of understanding the universe. I've looked at geophysics when I was trying to understand whether the Earth could be a source of antineutrinos, a weird kind of new elementary particle, and so anything is fair game for me, any aspect of nature, and I enjoy learning new things in order to support my research. I also enjoy learning new things in order to be able to write about them too. So both my writing and my research prompt me to study new things about the universe, because I find the whole thing to be fascinating, not just one part of it.
Okay, so our second question actually was about your PhD life and PhD topic, but you answered something about PhD.
Let me add some questions about some answers about my PhD life, because there's another aspect of that. I started doing mathematical physics. I was very mathematical, and when I started my PhD, I was working on very mathematical areas of physics, something called the mathematics of gauge theories and fiber bundles, and and it turned out that I found it not very satisfying ultimately in what I was working on, and a friend of mine now, who was a professor who was a professor I met at a summer school and then got to know, named Sheldon Glashow, who happened to win the Nobel Prize in Physics for helping unify the weak electromagnetic interactions, at one point said to me that, there's formalism and there's physics, and you have to know the difference. And I realized that I was much more satisfied if I worked on things that had a contact with experiment in some way, contact with measurable aspects, and trying to understand the phenomena, because the questions that physicists ask are different than the questions that mathematicians ask. It's not as if the questions that mathematicians ask aren't interesting or important, but they're different. And so I felt that in order to make progress in physics, I really had to try and keep contact with the phenomena to try and understand what was happening in accelerators at the time, and then ultimately in measurements in cosmology. So, and it wasn't a very pleasant time either. I switched. The PhD is not necessarily a time of a lot of fun. You feel you're switching from taking classes to beginning to do research. It can be very tentative. It's easy to feel insecure, and I felt all of that. I actually switched supervisors. I thought of quitting physics during that period. I almost went back into the medical degree in a moment of real despair.
Oh, really? We didn't know this at all.
Yeah. In any case, but I eventually continued, and also the other aspect that I think is important is that I didn't think I would get a job. There were not many jobs in physics at the time I was doing it, and I remember learning. I thought I was driving a taxi, probably, so I was prepared to do that. I also learned how to juggle in case I needed to work on the streets. So I didn't think I would get a job, but that didn't. And I say that because I think too many students worry about getting jobs, but it's the one time in your life when you can really do something you want. And so I did physics because I wanted to do it, and I didn't know whether I'd ever be employed doing it. But I somehow managed to work it out in the end.
So always, yeah, Rifat, go on.
Well, it's a nice history actually, and I would like to add something about that. Yep, I actually agree with you that people usually think about the work, what he can do with what he is studying, but I think, like you, that your interest can do everything for you.
Well, yeah. Well, I mean, keeping interested is what's important. And remember, during the hard times, and there are always hard times, during the hard times of any area of study, remember during that period why you're interested in what you're interested in, and let your interest keep you going during those hard times. That's my advice.
Yeah.
Okay.
I give
Thank
any.
you.
So, Professor, what do you think about the future of astrophysics and cosmology? Because when you started, it was almost new subject. So, what do you
Well, the
think?
area of particularly the area that I worked in, which is the intersection between particle physics and
Particle
cosmology, was
physics,
totally new. I was one of the, I don't know whether the word pioneer, but I think I wrote some of the first papers in that area. What do I think of the future? The great thing is I don't know what the future will be. And that keeps me going. People ask me what's the next. People often ask me what's the next big thing, and I always say if I knew, I'd be doing it.
Yeah, this
So
is an
the
excellent
universe
answer.
continues to surprise me. It has been a golden era in astrophysics and cosmology, with the onset of new instruments. Every time we open a new window on the universe, we're surprised, and we've had a whole lot from the Hubble Space Telescope to the cosmic microwave background detectors, both in the sky and on the ground, and now to gravity wave detectors. It's a wonderful time and an exciting time. So, but what the future brings, we'll see.
Okay. And last,
Oh,
yeah,
I have a question. Sorry, I have a question. That I know you are one of the first pioneer persons who talked about the dark energy in the primitive times. That what made you to think about the dark energy?
Well, first of all, let's see. I like to be heretical, so I like to go against the tide if I can, anyway. But more importantly, as I studied over many years, I was interested initially in dark matter because I wanted to know how the universe would end. I wanted to be the first person to know how the universe would end. Seemed like a good idea at the time, and so that got me interested. And the question always became one of, well, after the results of something called inflation, as I've talked about in my books, it seemed the only sensible possibility was that the universe was exactly flat. There was exactly enough matter to make the universe flat, which in a traditional sense would make if matter was all there is, would make the universe expand and slow down and never quite stop. That seemed the only rational possibility from a theoretical perspective, given the observations of the universe. But the problem is, as things progressed, it began to look clearer and clearer to me that there wasn't enough matter to make the universe flat. And there were other problems. And as I began to study this, I realized that the data didn't match. It just didn't hold up with the standard picture of a universe with a, as we say, omega equal 1, a density of dark matter. And it just didn't seem to work to me. And that took a long time of thinking about, well, what's the problem? And I was pretty convinced that the problem was that some of the data was wrong. And surely, in fact, we did live in an omega 1 flat matter-dominated universe. But so I began to look at the data, and in order to demonstrate that the data was wrong, I began to realize, well, what would fit with all the data, and very early on with some colleagues in the 1980s, when there were early problems with dark matter, I realized that one of the possibilities was that there was this dark, what is now called dark energy, but at the time a cosmological constant. But in the 90s, I started to look more detailed, and I realized that everything fit perfectly with this ridiculous idea that 70% of the energy of the universe resided in empty space. And when a colleague and I convinced a colleague of my friend Mike Turner that this was a possibility, and we began to investigate it more, and everything fit with this ridiculous notion. So we published that, and I published it primarily because I thought, well, look, everything fits with this ridiculous idea. We really need to show that at least one of the bits of data is wrong so the fit can go away. But in fact, we were exactly right. Everything fit exactly with the model that with the picture we presented well before it was observed, and it was very satisfying in the end to be right, even if they decided to give the Nobel Prize to the people who observed it rather than the people who proposed it. Anyway.
It is so strange. And what was your reaction on this?
Well, I think I told a reporter the first time I didn't believe it is when they observed it.
Okay.
I was so shocked.
Yeah.
But it was remarkable, and you know what? And I think it's an interesting bit of history of science, because this was a dramatic observation, which could have been wrong, the supernova observations. But within a very short time, the whole community accepted it, and I think it's because, in partly, I'm not sure I'm responsible for this, but the minds had been prepared that there was a problem, and this solved the problem, so it all fit. And that was really important. When people later on talk about maybe this dark energy isn't there because maybe the supernova observations are wrong, the point is it's not just one bit of data that points to it, it's everything. Everything fits together only if that's the case. So it's not one thing that may be wrong that would change everything. You'd have to say that basically all the observations in many different areas, from the cosmic microwave background to the structure of galaxies to the cosmic microwave background, that would all have to be wrong, and that seems pretty unlikely.
Yes.
Okay.
Yes.
I have another question actually. Though I have taken some time, but I have interest about this dark energy. I study a lot about this. So,
but I think just I am interrupting for 1 second, because we will ask everything. So you can start from the Big Bang, because according to our schedule. So maybe middle, then audience will be comfortable to listen step by step.
Okay.
Sure. Okay. We can proceed.
So go on, Rifat, go on. First question you can ask.
Actually, my question is about, I know you are working to make a relationship between the dark energy and the Higgs field. Though primitively you are the skeptical about the Higgs field. My question is, tell me something about your research on the Higgs field and the relationship between the Higgs field and the dark energy.
Oh, okay. Well, I have written about that. Well, yeah, I was very skeptical about the Higgs field, because it just seemed too slippery, too simple. I thought nature would be a little more imaginative as a way to solve the problems of the Standard Model, and I thought the Higgs field was just an allegory, if you wish, for what was really happening. And I was pretty convinced, therefore, the Higgs particles probably didn't exist, and I was hoping, I had several papers in ready for when they didn't see it, so that I could explain why it wasn't there. And then, darn it, nature said the Higgs particle is there. And like what's happened to me many times in my career, it's only after the observations are made, only after the measurements are made, that you really begin to think seriously about certain problems. There are many papers I've written that I could have written well in advance, but only after the observation was made did I begin to think seriously about it. I remember I wrote a paper showing there were only 3 types of neutrinos because of measurements in accelerators. And I could have written that paper years earlier, proposing that that would limit it, but I didn't think seriously about it until they actually measured these properties of the accelerators. And similarly with the Higgs. And once the Higgs was there, I began to realize that the fact that there's a scalar field in nature, that there's this invisible field everywhere, changes things. And if you take it seriously, there's a possibility that there are other kinds of scalar fields in nature that behave similarly. And I kind of realized that the Higgs, and I'm not the only one to realize this, that the Higgs could potentially opens up a window, or what's been called a portal, to a whole bunch of new physics at a realm that we might not be able to directly measure. And what I did, I wrote a paper that showed that, well, this dark energy in the universe, the value of the dark energy is so ridiculously small compared to particle physics standards that it's very hard to understand. But that in fact it's possible that if the transition that produces this Higgs field in the universe could couple to another transition that would actually produce an energy that's just the right magnitude to be seen. It's an ugly model. I would be amazed if it were right, but you never know. But I wanted to demonstrate that at least provided that possibility, and I also wanted to save the universe, which this model would do, because if the dark energy is really due to some field that's storing energy in the universe, and that field changes, that field melts, and that energy goes away, then the properties of fundamental physics could change and everything we see could disappear. And the whole universe could end as far as we know. But in my model, even if that's the case, it turns out everything changes by just such an imperceptible amount that we're still here. So I'd save the universe.
Okay.
But as I say, it's just I don't think it's a toy model that I think is unlikely to be correct. But in any case, it demonstrates that there are a whole set of new possibilities that open up once you have the Higgs field.
Okay. Thank you, Professor, for your explanation. It is very good, I think, and very easy to understand.
Yeah,
but,
actually.
But now I want to ask a question. I mean, on the behalf of school students,
Yeah.
So when we go to give seminar among the school students, they always ask that what is the birth, how this universe were born, and what is the possible physical reason behind it. So when we say about singularity, they don't understand, or they think that how it can be created from nothing. So what is
Well, I think no one can understand singularities, at least physically. Mathematically we can, but the fact that the whole universe was infinitely dense, and I mean, it just seems crazy. And probably not true. Probably most of us, I think that before that is because when the universe is that small, then quantum mechanics becomes important, and we don't have a quantum mechanical theory of gravity. So I think most of us think that something happens, that there's a new the fundamental theory will come into play, and we'll need new physics to describe the universe at that point. But as I pointed out, well, the question why did the universe begin, or how did the universe begin, and whether there was anything before our universe are questions we all ask. And there are two possible answers. The first one is that there is no before, that time and space are tied together, and if space suddenly comes into existence, so does time. So it doesn't make sense to ask what happened before. There was no before. But that's not very satisfying to anyone. And as I showed in one of my books and other things, it's quite plausible. In quantum mechanics, on small scales, many weird things are happening all the time. Particles are popping in and out of existence, and all the time. And if gravity is a quantum theory, gravity is a theory of space and time. So if gravity is a quantum theory, then even whole spaces can pop into existence by the laws of quantum mechanics and disappear. Whole universes can pop into existence. And if you simply ask yourself the question, let's ask if our universe could have popped into existence from nothing, what would be the properties of a universe that popped into existence based on the laws of quantum mechanics from nothing, that would last 13.8 billion years, And the characteristics of that universe would be precisely the characteristics of the universe we live in. So it suggests it's very plausible, even though we don't have a fundamental theory of the quantum mechanics of gravity, it's very plausible that our universe came from nothing. And moreover, you might say, well, that's impossible, because where did all the galaxies come from? There's 100 billion galaxies, and all of these, each of them contains 100 billion stars. And where did all of that come from? And the answer is that, well, it's like, as my friend Alan Guth says, the ultimate free lunch. Because it turns out that with gravity, you can have positive energy and negative energy. And the total energy of our universe, containing all 100 billion galaxies and everything, can still be zero. All the energy can add up to be precisely zero. And that means you can start out from nothing with zero total energy and create a universe which has a lot of galaxies which have positive energy because they have mass, but their gravitational attraction produces negative energy, and the two things add up to zero. So you can get everything for free. It seems like a scam, but it seems to be possible. And that's remarkable. That's truly remarkable. So to me, that certainly seems the most likely possibility, and it's quite plausible based on the laws of physics we know. Of course, we don't have an exact theory yet to explain that, but isn't it wonderful that that's possible without any supernatural shenanigans?
Yes. But
Okay.
Anyway.
Real nice explanation, actually.
What was that?
I was saying that it was a nice explanation to our school-going fellows.
Well, I hope so. It's still pretty hard to understand, and I realize that people may be scratching their heads. But that's okay. We're scratching our heads, too, because it's all right to not understand things and to not know things. That's what drives physicists.
okay,
Not knowing is a very important thing.
yes,
And we should all be comfortable with saying, I don't know, because that means there's more left to learn. And it all means we can all get together and answer questions. The process of education should be a process of discovery, and we can work through it together.
exactly. But on a serious note, that we can explain many properties of the universe after inflation. So let's say 10 to the power minus 35 second or something like.
Yeah.
So it is also very interesting that we can say after that very, I mean, when the time was young, I can actually say very, very young, we can exactly explain many properties by mathematics and by observation particularly.
Unbelievable. And
Unbelievable.
not only that we can measure it. When I was your age, when I was a student or a postdoc, and even a young professor, I never thought we'd be at the stage we are at now during my lifetime, where we can measure these fundamental properties of the universe and compare our theories to them and get such good agreement. It's a shock.
Yeah, exactly. But then
Indeed.
I wanted to ask one thing, that what do you think that how to explain the general public that how first stars and first galaxies were born in this universe, and also the large scale structure started to form?
Well, I mean, the gravity is naturally unstable, right? If you put a gas of particles together, they'll collapse, just like stars and galaxies do. And you have to set things up very carefully so that gravity doesn't produce lumps. Right? Almost any time when you look at something, there are lumps in it. You have to make it exactly smooth in order for gravity not to. If there's one little area that has a little more matter than everything else, it will clump together.
Yes.
And the same is true for electricity and magnetism too. By the way, when you look at the sky, when instabilities produce clumps all the time. You don't see snow in Bangladesh probably, but when it gets cold, you see snowflakes because small imperfections, small dust particles cause the water to want to coalesce either into raindrops or snowflakes. And the same is true for gravity. So in the early universe, if there are unless things are exactly uniform, you expect gravity to cause things to clump. What's amazing is not that there are clumps, but that they didn't form earlier, that the universe is as uniform as it is. That was a mystery. In the early